So first of all, welcome all to this lecture about electric machines and drives. It is a continuation of a course that you probably have about actuation systems in your bachelor or equivalent if you come from abroad. And today I will give you a short introduction on what is electrical power engineering and then on the electric drives, and then we will go on the mechanical requirements to have and then we do some simulations. So here I will start to record this, and then I will make some just small records from each chapter. So it will not be a long 3 hours video, but just some 10 minutes videos that I will put on Canvas. So let's start recording. Introduction to power engineering. So power engineering, it is a study of electrical energy, and it consists in 3 parts, which is production of electricity. The second is transportation and distribution of the electricity that is produced. And the third part is how to utilize the electricity. So electricity can be produced from different sources. Either nuclear energy, which is produced by nuclear power plants, or fossil fuel, which are coal power plant, or petrol or natural gas, or wind power, so wind turbine, and this now we are going to the renewable energies. So it's wind, and then it's PV cells. And lastly, it's also hydropower. And here we need a dam and a reservoir. And as you might know, in Norway, we have 98.5% of the electricity, at least in 2008, that was produced by hydropower. So here is a map, and you can see what the sources of electricity production for each country. And here we see that in Norway, it's 1.49 terawatt hour that is produced. And out of it, it's 142 that is coming from hydro. And we also have a flow where we export and import electricity from other countries. But the main component in almost all power plants is a generator. So the exception is for PV cells. We don't need a generator. And this generator is a rotating machine that transforms mechanical energy into electrical energy. And this is created by a movement of magnetic field inside, or it's a relative movement between the magnetic field and the electrical conductor with current. And we will look into this a bit later. So that was the first part. And now that the electricity is produced, then we need to transport and distribute to the users. And for this, we use a smart grid, and it consists of a generating station where we produce energy, and then we need to transport this to the primary and secondary customers. And if we are using low voltage and high current, that will give us a lot of losses, because we have ohmic losses that are equal to R times I square. So what we want is to transform this electrical power into high voltage power and low current. But on the other hand, also, we don't want to have too high voltage, because then it will increase the price of the components. So usually we use about 400 kilovolt to transport the energy. And to convert this voltage to high voltage, we need transformers. So power transformers and then distribution transformers to step down the high voltage into, for example, 240 volts in each houses. So all of this system of transmission lines, it's called the power grid. And then the third part in power engineering is utilization of electricity. So different way to use electricity. One is using thermal energy. It's like industrial oven or heating systems for buildings. Second one is light to have light in every building and houses. So this is 18% of all electricity that is produced. Another one is chemical energy, for example, electrolytes. And then we also have electronics. And finally, we have electrical motors. And electrical motors, they are using 46% of all electricity that is produced. So if we manage to have every motor in the world 1% more efficient, that will be a lot of savings. And these are the parts where we are interested in this course. So namely the electrical machines or motors and generators. So these motors are used more and more, I would say, because we are moving towards a very electrical economy, where we have electrification of transport, for example. And then this requires batteries, and we have a tsunami wave of lithium-ion batteries that is coming. And if we look at electric cars, for example, we see that especially in Norway, it's increasing a lot the last 10 years. Starting from 2011, then we see that the market share for new EVs is increasing much faster in Norway than in the rest of Europe. And the last numbers for 2020, it was that more than 50% of the new builds of the new cars, are electric in Norway. And now we have in 2020, it was 230,000 new cars. No, I think that's the number of cars that are of electric vehicles in Norway by 2020. But it's not only electric cars. It can motors are used in, for example, everything from e-scooter to, for example, e-skateboard, but also train or electrical ferries. Just in Norway, now in 2020, it was built 20 new, or 60, sorry, 60 new e-ferries. And then soon will come also the electric airplanes. For example, Boeing is planning to have, by the end of the 20s, hybrid electric airplane, but also fully electric shortly after, I guess. Okay, so now I stopped recording. And that was our first chapter, which was a just introduction of electrical power engineering. If you have any questions, you can now ask or leave a message on the chat. Then, if no questions, I will go to the next, which is electrical drives. So I will start recording again. So this is a short introduction on electric drives. So an electric drive is a smart converter or transformer that converts electrical power from a fixed form, for example, 50 hertz, 3 phases, 230 volt or 400 volt, into mechanical power with variable form, because we can have a variable speed and also a variable load torque. And this is done by using a power processing unit, or we can also call it a power electronic converter, PEC, that delivers appropriate form of frequency and amplitude and phase of AC voltage into the motor or the machine as required by the load. And this is controlled by using a sensor. So we sense speed and position, but also the current inside the motor. And then we use a controller to given a reference input or command, which can be speed or position, but also torque. It will communicate with a PEC or PPU here to give the correct form of electricity that is sent to the motor. And this architecture is the same for all electric drives, but each motor can have several types. So we have categorized these motors into 4 groups here. The first one is asynchronous motors. These are the most used motor in industry. And we have 2 types. It can be wound rotor induction motors that are easy to start, or squirrel cage induction motors that are very simple construction and robust, and that can also be used now with a variable frequency drive to have good performances. But if we want to have extra best performances, maybe the synchronous motor with a permanent magnet is the best choice. And this is typically used in robotics or in application when we need a high efficiency and precision. And we can also have a synchronous motor in a high power application, like for example, train. And that will be used with a transistorized variable frequency drives. The third step is DC motors. And today is less than 40%, but it was much more in historically when before the power electronics was invented with a semiconductor, then most of the electrical motors were DC motors. And it still takes time to remove all of them, I would say. We can have a low power DC motor and also high power DC motor. And the last category is step motors, which have quite low power, but they can be very compact and can be used for mostly for position application or positioning application. So these electrical motors can be used in a very large range of speed, up to 80,000 RPM, but also in a large range of torque and power. So it can go from 1 watt to 100 megawatt. The main advantage of electrical motors over fuel or combustion engine is that they can operate in any operation conditions. Like if we have it can work under the water in some application on explosive atmosphere or in outside on the rain. Also, we don't need to refuel them. There is no exhaust and a very low acoustic noise level. They also have a high efficiency and can be bidirectional. It means that they can regenerate electricity when it's breaking. And here also another way to categorize a motor by the power. We have a small motor that are between 10 watt and 750 watt. And then we have the medium size. And then we have the large motors that have more than 375 kilowatt. So we see that the electricity that is used is mainly used by a middle-size motor. It's 68% of this 48% of the whole electricity. And approximately 230 million pieces of such motors. And we can see here that it's asynchronous induction motors with 2, 4, 6, or 8 poles mainly. We can also have these special motors that are DC permanent magnets or switch reluctance or step motor. So the category that we have seen before. So these electric drives, they are actually combining different areas of engineering. We need to understand the mechanics of rotating machines. And that will be the goal of this first lecture afterwards. Another area is electrical machines. So to see how the motor is modeled and to understand the properties and how to design the control systems. So that's the goal of lecture 2, 3, 5, 6, and 9. And then we also have power electronics to see how this principle and limitation of power electronic converters. It's lecture 4. More about control engineering, and this is done in lecture 7 and 8 in this course. And we also have other engineering areas that are sensor and measurements, and signal processing and computer engineering, and these are not covered. So the main challenges that we will answer in this course, then we will go beyond what we have seen in the Bachelor Electrical Actuation course, which was focusing only on steady-state operations. Now we will look at the dynamic response of AC machines and how to simulate the dynamic or the motor or generator and see the dynamic response. That's lecture 5 and 6. And what we have seen also in the Bachelor course is how to control the steady state operations of electrical motors by using this V divided by F ratio and a PI controller. But it's to make it much responsive and performant, we will use another type of control, and this will be done in lecture 7 and 8. And then we will also look on how the output signal of a linear controller can be converted into a suitable switching signals. So how to go from DC to AC signals using switching mode. This is done in lecture 4. And the last challenge is how to optimize the selection of components, because we have a PEC, motors, gearbox that are available in catalogs. And what we want is to find the best combination of this. And we will reuse some of the lecture 1, but mainly we will look at it in lecture 9. So this, now I've stopped the record. So that's a second chapter. And now you also have some time for questions if you have. Can you all understand what I say, or is it difficult with my accent maybe? Yes, it's all right, okay. So next is, I think we can, even if it's only 40 minutes now, yeah, actually just half an hour. But I will, yeah, let's have a 10-minute break. And then we can start again at 10 to 10 in 10 minutes. So you can make a coffee and come back, for example.